So today we're going to start on radiation. Radiation, big scary radiation. All right. So I know it's quite hard to understand, but just like everything else, just like all the other modules, there's similar types of questions that come up every year. So if you know how to do those, even if you don't fully understand, if you have at least a basic understanding of how to what to recognize and which equations to use, then you should be fine. Okay, so I'll go through all of the common questions. Okay. So number one, we have an electron, which is so before I begin, I'll just quickly kind of revise some basic chemistry, which you'll have to know. So this is the mass number, right? So you have your chemical element symbol. So that's your chemical element, and then the symbol A is going to be your mass number. So that's the number of. So this is the number of nucleons. Okay, so nucleon. So you have a proton. You have protons and you have neutrons. Okay, so both of these are what we call nucleons. Okay, so this is the mass number. Okay. And then, so this letter Z on the bottom here, this will be the atomic number. The atomic number, and that tells you the number of protons. Okay? So that's the number of protons. So if you've got the number of nucleons and the number of protons, then you can work out the number of neutrons, which will just be the difference between them, right? Okay, so I'm pretty sure everyone already knew that, but just making sure that everyone's on the same page. Okay, so we have an electron initially in an atomic energy level. So it's in the 4th orbital. Okay, so the initial N is 4. Okay, so here's our nucleus. All right. So our nucleus contains the protons and the neutrons. All right, and then you're going to have your first orbital, your second orbital, your third orbital, and then your fourth orbital. Okay, so our electron, so this is n equals 1, n equals 2, n equals 3, n equals 4. Okay, so you've all been doing Chem 191. I'm sure you're more than familiar with all of this. Okay, so our electron starts in our 4th energy level, and then it drops down to n equals 1. Okay, so this is the ground state. Okay, this is the lowest energy orbital, which means that when it jumps down, it's going to lose energy. So when it comes down, there's going to be a change in energy. And so because that energy can't just disappear, energy is going to be emitted in the form of a photon. Okay, so we've got a photon coming out. So that photon, it has a frequency. So it has a frequency which is equal to 3.08 times 10 to the power of 17 hertz. Okay, Now, the atom is hydrogenic, so what that means is that there's only one electron. So if there were a bunch of electrons in these orbitals, then it would make the equation much more complicated, because then you'd have a shielding effect, which we're not going to go into, but just as long as you know that it just means that there's one electron surrounding this atom, and that's going to make your calculations a lot easier. And that's pretty much all you need to know. Okay, so we know the frequency of this photon. Now the first question there is, what's the wavelength of the emitted photon? Okay, so photon is a form of electromagnetic radiation, or light. Okay, so light is a wave, which means that the velocity of a wave is equal to frequency times the wavelength, right? So the velocity of electromagnetic radiation, or light, is going to be c, right? So c is equal to 3 times 10 to the 8 meters per second. Okay, so by exam time you should be able to memorize that, but that's going to be on your formula sheet. Okay, so that means c is equal to frequency times the wavelength. Now we know c and f, so we want to find out the wavelength. Okay, so wavelength is equal to c divided by frequency. So 3 times 10 to the 8 divided by a frequency, 3.08 times 10 to the 17, and that will give you 9.74 times 10 to the negative 10 meters. Okay, and then to turn that into nanometers, you have to divide by 10 to the negative 9. So divide by 10 to the negative 9, that will turn it into 0.97 nanometers. Okay, so the next question is continuing on from our first question. So we want to find out the difference in energy between these between the two atomic energy levels. Okay, so for a photon, you have the frequency, you have the wavelength. So you have frequency, you have wavelength, you have the energy, and you have the momentum. So momentum. Okay. So a photon can have all four of those things, and if you know just one of them, you can calculate the rest of them, because they're all interconnected by Planck's constant and the speed of light. So we want to find out the difference in energy of these two atomic energy levels, so we want to find out what delta E is. But we can't do that using the normal equation, because we don't know how many protons this nucleus contains, so we don't know Z. Okay, so we don't know the atomic number, so we can't use the delta E equation. But what we can do is we can use the frequency, or we could use the wavelength that we just calculated to figure out what the energy of the photon is. And remember, the energy of the photon is going to be exactly the same as the difference in energy. Okay, so we'll figure out the energy, and we're just going to use the frequency because that's easier. Okay, so energy is equal to HF. Okay, so H is Planck's constant. This is also on your formula sheet. So H is equal to 6.63 times 10 to the negative 34. Okay. So that means your energy is equal to 6.63 times 10 to the negative 34 times your frequency, which was 3.08 times 10 to the 17, and that will give you 2.04 times 10 to the power of negative 16 joules. Okay, so that's going to be option B. Now it's a little bit off because just because of rounding, but that's close enough that, and it's way closer to option B than all the other options. Okay, so I'll just quickly show you how you could have calculated that using the wavelength. Okay, so we know what the wavelength was, so we knew that it was, the wavelength was 9.74 times 10 to the negative 10 meters, right? So energy is equal to hc over the wavelength, okay? So h is Planck's constant, c is the speed of light. So E is equal to 6.63 times 10 to the negative 34 times the speed of light, which is 3 times 10 to the 8, divided by the wavelength, which is 9.74 times 10 to the negative 10. And that should give you the same answer of 2.04 times 10 to the negative 16 joules. Okay, so you have two options there. And if you look on my cheat sheet that I've put up on the Google Drive, which is here, all the equations for your photon is along the top line here. So I know you can't see it, but if you go on my Google Drive and have a look, the line along the top is just everything rearranged. Okay. So we found the difference in energy, which is 2.04 times 10 to the negative 16, or 2.03, it doesn't really matter. So we'll leave that. So I'll get rid of this, and so I'll write that number up. So the energy is equal to, so that's the change in energy between the two atomic energy levels. So that's 2.0, we'll just say 2.03 times 10 to the negative 16 joules. Okay, so the third question, which is following on from our question stem, is what is the atomic number, Z, of this atom? So remember, the atomic number is the number of protons within this nucleus. And so the energy difference between these energy levels is going to depend on the number of protons in this nucleus. Because if you think back to electricity, you have a negative charged electron and a positively charged nucleus. Okay, so if you have a negative charge further away from a positive charge, that's going to have higher potential energy, right? And then if you bring it closer, that's going to have lower potential energy. And if the nucleus has a greater positive charge, that difference in energy will be greater because you've got more pull, you've got more positive charge pulling that electron in, so there's going to be greater energy. Okay, so that's what we want to find out. So this is a big equation. So Z is equal to the square root of the change in energy over, so bracket, so the final orbital level to the power of negative 2 minus the initial orbital to the power of negative 2, close bracket, times 13.6 times EV. So EV is electron volts. Okay, so I'll just write that up here. EV is electron volts, electron volt. Okay, and that's equal to 1.6 times 10 to the negative 19 joules. Okay, so that's a unit of energy. All right, and the reason we do that is because when we're talking about radiation, all of our quantities are so small, so that's just a really small unit to make it easier to deal with these small quantities. Okay, so this EV, you're just going to, because we have our energy in joules, we need to replace this EV with 1.6 times 10 to the negative 19. Okay, if we had our energy in units of electron volts, which can happen, then you wouldn't need to put 1.6 times 10 to the negative 19 in there. Okay, so let's put our numbers in. So delta E was 2.03 times 10 to the negative 16 divided by our final orbital, which was 1. Okay, so 1 to the power of negative 2 minus our initial orbital, which was 4. So 4 to the negative 2, close bracket, times 13.6 times 1.6 times 10 to the negative 19. Okay, and that will give you a number of 10. Okay, so that means there's 10 protons in that nucleus. All right. Okay, so our next 3 questions are pretty much exactly the same. So that first page came up in 2015, and then this next page is in 2017. Okay, so that's pretty much exactly the same questions. So we have an electron in initially this time it was in the 3rd energy level. So it was in the 3rd energy level, and then it came down to the ground state orbital, which is n equals 1. Okay, and then when it made that transition, it's going to emit a photon. Okay, and this time we've been told the wavelength of the photon, and we want to find out the momentum of the emitted photon. So the relationship between momentum and wavelength is this. So the momentum P is equal to h divided by the wavelength. Okay, so h is 6.63 times 10 to the negative 34. That's our Planck's constant. And the wavelength was 11.4 nanometers, so we have to convert that into meters. 11.4 times 10 to the negative 9. And that will give you 5.82 times 10 to the negative 26 kg meters per second. Okay, so that's the momentum. And remember, if you know one of the 4 things, momentum, wavelength, frequency, or energy, you can find out any of the other 3. Number 5, we want to find out the magnitude of the difference in energy of the 2 atomic energy levels. So remember, we don't know the number of protons in this nucleus. So we need to use the energy of the photon. Remember that the energy of the photon will be equal to the change in energy. So we could use, I'll show you both ways. So first we're going to use the wavelength to calculate that energy. So the change in energy is equal to the energy of the photon. Okay. And the energy of the photon is equal to hc over the wavelength. Okay, so 6.63 times 10 to the negative 34 times our speed of light, which is 3 times 10 to the 8, divided by our wavelength, which was 11.4 times 10 to the negative 9. Okay, and that will give you 1.74 times 10 to the negative 17 joules. Okay, and then you could also use the momentum to calculate your energy. So energy, the energy of the photon is equal to momentum multiplied by the speed of light. So that would be, the momentum was 5.82 times 10 to the negative 26 multiplied by our speed of light, which is 3 times 10 to the 8. And that would also give you 1.74 times 10 to the negative 17 joules. Okay. So it doesn't matter which one you use. Now, number 6, we want to find out the atomic number, or Z, of this atom. So we're going to use the same equation. We need to know the change in energy. And the change in energy was 1.74 times 10 to the negative 17 joules. Okay, so Z is equal to the square root of delta E over NF to the negative 2 minus Ni to the negative 2 times 13.6 times the electron volt. So our change in energy is 1.74 times 10 to the negative 17. Our final orbital level was 1. Okay, so 1 to the power of negative 2 minus our initial n, which was 3. So 3 to the negative 2 times 13.6 times our electron volt, which is 1.6 times 10 to the negative 19 joules. So that will give you 3. Okay, so you'll have 3 protons in this nucleus. Okay, and so okay. So it's always going to be a whole number. Don't worry if your calculator says like 3.0023 or whatever, something. But the answer will always be a whole number because you can't have a fraction of a proton in your nucleus. Okay? All right. So we'll move on. Rub this off. Number 7, the energy of copper K alpha X-ray photons is 8.0 kilo electron volts. So remember, electron volts was our unit of energy. So that's 8,000 electron volts. So energy is equal to 8 times 10 to the power of 3 electron volts. So electron volts is the unit of energy. We want to find out the momentum. Okay, so our equation for the momentum of a photon is equal to the energy divided by the speed of light, c. Okay, so this energy has to be in joules, not electron volts. So we need to convert electron volts into joules. So the way we're going to do that is to multiply it by 1.6 times 10 to the negative 19. And that will give you, I don't actually know what that gives you, but we'll just do it up on here because I do it like this. So 8 times 10 to the 3, and we're converting it into joules by multiplying it by this number. and then divide it by the speed of light, which is 3 times 10 to the 8. Okay, and that will give you 4.3 times 10 to the negative 24 kg meters per second. Okay, so just remember your units. It's important. It has to be in the right units. Number 8, we have an alpha particle. So who can tell me what an alpha particle is? What's an alpha particle? So it's this thing here. So, yep, so it's got 4 nucleons. Yep, so it's helium. It's basically a helium atom without the 2 electrons. Okay, so a helium atom would have 4 nucleons, so 4 neutrons and protons, and it's got 2 protons, so it must have 2 neutrons. So it's basically 2 protons and 2 neutrons. Okay, so that's what an alpha particle is. All right, so if it's got 2 protons, the charge of an alpha particle will just be 2 times the charge of 1 proton, right? So the charge of 1 proton is 1.6 times 10 to the negative 19 coulombs. So that would be 3.2 times 10 to the negative 19 coulombs, and it would be positive, right? So that's your charge of an alpha particle. Make sure you remember that or write it down. So we want to find out the kinetic energy after it's been accelerated through an electric field, and in the electric field it's traveled through a potential difference of 80 kilovolts. Okay, so be very careful not to get mixed up with kilovolts and kiloelectron volts. Okay, because it can be, if you read it fast and you're in a rush, then it can be quite easy to make the mistake. Okay, so here our change in voltage. So our voltage is 80 kilovolts, so 80 times 10 to the 3 volts. And we want to find out the kinetic energy. So if you remember from electricity, hopefully you do. And so then the kinetic energy of a charge is going to be equal to the electrical energy, the electrical potential energy that it had. Okay, so the kinetic energy is equal to U, which is our symbol for electrical potential energy, and U is equal to Q, our charge, multiplied by the voltage. Okay, so pretty simple, 3.2 times 10 to the negative 19, which is our charge of the alpha particle, times the voltage difference, which is 80 times 10 to the 3. And that will give you 2.56 times 10 to the negative 14 joules. Okay. So if they tell you about an alpha particle, just remember that you do know the charge. It's just going to be the charge of 2 protons. So now we have binding energy. So the binding energy of an atom is the difference in energy between when all the protons, neutrons, and electrons are bound together and when they're all just unbound or separate. Okay, so if you add up the mass of protons, neutrons, and electrons, and you compare it to an atom, which is bound, there's going to be a difference. So all of them separately will weigh more than the bound atom. Okay, and because of the famous equation that I'm sure you've all heard of, E is equal to mc squared. Okay, or in this case, the difference in mass times the speed of light squared. Okay, so what that means is that mass is pretty much energy. Okay, and if you have a change in mass, that means you have a difference in energy, and that's our binding energy. Okay. And I find like people might find this quite hard to comprehend, but basically photons, so photons are energy, and when you heat up, you're gaining thermal energy. Okay, so that's increasing your thermal energy. So if you're increasing and absorbing energy, then you're absorbing photons. So photons are energy, and then they are converted into mass. Okay, so if you are heating up, then you're gaining mass, but it's like very, very, very minuscule. Okay, so it's so tiny, unless you were to, but like the change in mass would be so tiny because you're multiplying it by the speed of light, which is 3 times 10 to the 8 squared. Okay, so that's why a very little amount of mass can result in a lot of energy, which is why atomic bombs can be so powerful. Okay, so that's a bit of a tangent, but if it helps to understand, maybe it's not. So what we need to do is we need to find the total mass of all the protons, all the neutrons, and all the electrons when they're on their own. Okay, so first of all, we need to figure out exactly how many neutrons, protons, and electrons it has. So we've got 94, 47, and Ag. So Ag is the chemical symbol for silver. That's not really important. So we know that we have 94 nucleons. Okay, so nucleons include protons and neutrons. And we have 47 protons. Okay, so the number of neutrons is 47 protons. So if we have 94 nucleons, our number of neutrons will just be 94 minus 47, right? So 94 minus 47 is equal to 47 neutrons as well. Okay, and it's going to be a neutral atom. So that means that there's going to be the same number of electrons as protons. So there will also be 47 electrons. So that's great. We've got the number of protons, neutrons, electrons. So now our mass, unbound. So this is the unbound mass. So 47 times 1.007276. So that's the weight of the mass of a proton, plus 47 times the weight of the mass of a neutron, which is 1.008665 plus. So now it's electrons. So 47 times 0.000549. Okay. So that's going to equal 94.77503, and the unit is AMU, or well, they've just abbreviated it to U, but it stands for atomic mass units. Okay, I'll just write that up here. So, that's a lot of information. So we've got 1 atomic mass unit is equal to 1.661 times 10 to the negative 27 kilograms. Okay, so you can see it's a tiny amount of mass. And 1 atomic mass unit is equal to 931.5 mega electron volts. So remember, electron volts is our unit of energy, and that's mega. So mega is million. Mega electron volts times C to the negative 2. Okay, so mega electron volts over C squared is another unit of mass for radiation. And so if you look at the units that they want our energy in, you'll notice that it's mega electron volts. So they want our energy to be in mega electron volts, and that's going to come in, this is going to come in handy soon. Okay, so we want to turn atomic mass units, we need to turn that into this unit here. Okay, so to do that, we're going to multiply it. We're going to multiply it by 931.5. Okay, and that will be, oh, sorry, my bad. Sorry, I skipped a step. We'll come back. So this is the mass, the total mass when they're unbound. And now we need to calculate the difference between the difference in mass between bound and unbound. So that's going to be 94.77503 minus the atomic mass of silver 94, which is 93.943. Okay, and that will be 0.83203 atomic mass units. Okay, so that's the difference between bound and unbound. And now we're going to multiply that by 931.5. So we're turning it into this unit here, mega electron volts. And that will give you 775 mega electron volts, which is your answer. Okay? So whenever they ask for the binding energy, usually it's going to be in the units of mega electron volts. Okay? So all you need to do is find out the mass difference in atomic mass units and then multiply that by 931.5 and you've got your answer. Okay? So next we'll move on to alpha decay. So, which one of the following particles is produced in the decay of 235 uranium to 23190Th? So we've got 23592U going to 23190TH. So we want to find out what sort of decay this is. Okay, so if you look at the atomic number, the mass number and the atomic number, so what's happening is that you've got the mass number is being decreased by 4, so A minus 4. And the atomic number is decreasing by 2, right? and it's turning into a new. So whenever the number of protons change, that's going to become a new element. And so what that means is that it's lost 4 nucleons, it's lost 2 protons and 2 neutrons. So what's that? Yep, an alpha particle. So that's an alpha particle that it's lost. So it's going to be producing an alpha particle, or A, and that's called alpha decay. Okay. All right. Number 11, the atomic number of polonium is 84. So the atomic number, remember that's the number of protons. And polonium 210. So that's 210 is going to be the number of nucleons, or your mass number. Okay, so here's our mass number, 210, which is the number of nucleons, and 84, which is our number of protons, our atomic number. So PO, okay. Now it's going to decay by alpha particle emission. So what's the decay product? So what will the top number be? So 210 minus 4. Yep, so it's going to be 206. And it's going to lose 2 protons, so it's going to go from 84 to 82. So you just look for the option that has 206 and 82. You don't have to know which element it's going to be. Okay, so it's going to be PB, which is the element, the symbol for lead, but that's not important. The important thing is the numbers, so that's going to be option E. Okay, and because you're going to be producing an alpha particle, okay, which is 2 protons and 2 neutrons. So last one, again alpha decay, just for good luck. You've got 234, uranium 234, and it's got 92 protons, and so it's going to be alpha decay. So 234 minus 4 is 230. 92 minus 2 is 90. Okay, and you're going to look for the option that has 230 and 90. So that's going to be option E again. All right, and that's also going to produce an alpha particle. Okay, so in the advanced tutorial, we'll just go over some more binding energy and energy levels, and also some beta minus and beta positive decay as well. Okay, so we'll start again in 10 minutes at 8:25. Thanks.